today we'll talk about a testable scenario of WIMPZILLA with dark radiation.
Exotic creatures, WIMPZILLA and dark radiation. I want to make both of them and use of them for experimental data. And this is based on the paper with my postdoc, Seong Chan. Let me start from the WIMP. Probably most of you like the WIMP as the best candidate of dark matter. WIMP should be around the electronic scale. However, the most model independent bound for WIMP is actually around 100 TeV from unitarity. Just consider the annihilation cross-section, which goes like 1/n squared, and from that you can calculate the relic abundance of WIMP, and you can find the bound is around 100 TeV. This bound is robust as long as dark matter is in thermal contact with the standard model. So this bound is really robust. And if you assume that the coupling of the WIMP with the standard model is just like the standard model weak interaction, then the bound becomes 1 TeV because the cross-section now goes half a square of it. Okay. So using the dark matter data, you can set the upper bound for the WIMP models. And for instance, you can set the upper bound for the 1/r, the size of extra dimension for the lightest color Chung-Yuan dark matter, and also for the Suji models too. Okay. And probably this is the most latest result from CMS and other experiments. This is for the spin independent search, and this is from the spin dependent search. As you can see, LHC already gives the best bound in this energy range around 1 GeV, and this will be improved a lot in coming years. So I believe this whole region below the 1 TeV will be covered in some way. Okay. But this situation may be a little bit disappointing because we cannot go beyond 1 TeV, and 1 TeV, the window is almost covered by experiments. So probably we are motivated to think of other possibilities. Nature may not enjoy the beautiful WIMP framework. So how we can go to beyond the WIMP idea? The simple idea is actually this. Just rely on non-thermal production of heavy particles. It is well known that heavier particles can be produced in inflaton decay. In many stages of inflation the dynamics, you can find the heavy particles. And it is really interesting to see that there exists a unique window around 10 to 12 to 10 to 14 GeV out of this interesting inflation idea. If you just take gut scale inflation, then you will find some window of particle, and it is extremely plausible that you can have many particles in this window. And even more interestingly, the particle in this window can fit the dark matter abundance. Okay? And this dark matter is called WIMPZILLA. Let me call this WIMPZILLA miracle. So now let's take the WIMPZILLA as the dark matter, which is good, right? But still, the WIMPZILLA idea has some problems. First of all, the stability is a big issue. Any kind of heavy particle easily decays unless forbidden. Just take a look at the uncertainty relation, and you will see that the decay rate is proportional to the mass. So heavy particle can decay easily. And also, if the WIMPZILLA is around 10 to 12 to 10 to 14 GeV, there is no way to probe it experimentally, right? And I don't care any kind of theory which never get tested. So my suggestion is this. Let's think of the stability of electron first. Why electron is stable in the standard model? The answer is this, U1ENM. Okay? Electron never decays because it is the lightest charged particle of this U1ENM. And this U1ENM, as long as this U1ENM is exact, then we know that electron never decays. So electron is stable. So why don't we introduce another U1 for this WIMPZILLA? Actually, there are many U1s in theory, like the God or the string theory, whatever. You can find many U1s, and I just assume that one of these U1 is responsible for the stability of WIMPZILLA. That's the idea. Then the new gauge boson associated with this new U1 symmetry provides observational consequences. Okay? So now, both problems, stability issue and testability issue, are all solved just by introducing U1 for the WIMPZILLA. By the way, why I want to introduce U1 gauge symmetry for stability of WIMPZILLA? Maybe you are happy with the global symmetry like C2, right? However, if you consider the gravity, also the black holes, you can find that the global symmetries are not good. It doesn't work. So for more ambitious setup, you want to make the symmetry as a local symmetry, and U1 is the simplest possibility I want to use. So now, the issue is the dark radiation. So I introduced U1, so I have the new gauge boson. Okay? And this new gauge boson doesn't couple to the standard model particles, so naturally I call it dark radiation. Okay? It is massless photon, so it is dark radiation. And there have been several observations recently. Okay? And people call neutrino species or dark radiation and found the numbers like this. According to Planck, the number of neutrino species is this, 3.3. According to the WM9, it is 3.8. According to the BBN data, it is 3.7. So you can see that there is a room for the dark radiation. So now the model building. So the question is, can my dark radiation or hidden photon play the role of dark radiation? The answer is yes. Dark radiation from the late time decay or particle is the answer. If you consider a particle which decays at the right moment, then I can really explain the amount of dark radiation I showed you. So for instance, if a particle decays around BBN time and produce dark radiation, then this guy is observable. Also, if a particle decays around the CMB time, it also explains the dark radiation. Okay? So this is the only diagram I'm going to use. So this is the particle which I introduced, and WIMPZILLA in the loop, and this is the dark radiation. As you can see, the dark WIMPZILLA is so heavy that the decay rate of this guy is highly suppressed, like 1/m psi square. And here m psi is the mass of WIMPZILLA, which is 10 to 12 to 10 to 14 GeV. So if you calculate these numbers, you will get the reasonable numbers for the EDN, also the CMB. So this is the model. So here, X is WIMPZILLA. Okay? This WIMPZILLA is stable because of the U1. And phi is U-scalar particle, which is long-lived. And this decay of this guy is determined by the rest of the WIMPZILLA. This is dark photon. And this is my simple Lagrangian. Okay, this is U1 invariant Lagrangian. And this X has a mass because this is the Dirac particle, so it naturally has a big mass. And it also has the Yukawa type interaction like this. And the dark photon has the kinetic term, and my new scalar has this kinetic term. You may allow those two U interactions if you would like to use them. And I will use one of them actually. So let's discuss more about this. So this is the most general, anomaly free. We normalize the Lagrangian of this type. And here I just use Dirac particle for the WIMPZILLA because unless forbidden, the Higgs photon type interaction will give you the mechanism of the decay of this WIMPZILLA. So I want to use the Dirac particle. And also, I want to neglect this because I don't introduce no bicharged particle. But if you like to use the bicharged particle, then you will allow this epsilon 2. That's another phenomenology. So now here I calculated the effective number of neutrino species. And here I add the standard model contribution, which is 3.04. And the contribution from the phi decay, which is here. And also the contribution from the primordial hidden photon, which is 0.05. So this number is negligible. So having all these things, I can fit the data. And this is the parameter space I can have. So here is the mass for the new scalar particle. And this is the coupling between the new scalar particle and mass. And this regime is excluded, already excluded, because here in this regime, the Higgs invisible decay is too big, so this region is excluded by the LHC data. And as you can notice, in this energy range, like 10 GeV, you can have some sizable amount of effective neutrino species, so you can actually explain what we have observed. So let me conclude. The upper part is from the Loki Cole's old talk. So first of all, origin of inflationary perturbation from creation of particles is from the creation of particles in the expanding universe. That is good. And beautiful ideas often have other applications, and WIMPZILLA is too. Perhaps origin of dark matter also from the creation of particle in the expanding universe, from the decay of inflaton. Okay? And now in this talk, I showed you that dark matter shows its presence in the dark radiation and also Higgs invisible decay. That's it. Thank you very much.
Questions?
Include the Lagrangian. So I wonder why you don't have a height Q and
You mean the potential of this side?
and also
So here, the only issue is whether this side develops back or not.
yeah.
So here, I didn't allow the bath, but of course you can allow bath, then it doesn't play as I like.
The phi cannot leave long, right?
Yeah, that's right. So once this guy develops bath, then I cannot explain why the longevity of this guy.
Well, one question now. LHC rules out some final space.
Yes.
Only the lambda phi edge and
Yes.
and it's in that.
That's right.
That's right.
That's right. That's right.
Other question?
Yes.
I'm not sure, how do you produce the phi particle?
Phi particle. I allow this, so this phi is in thermal contact with Higgs. So in the early universe, it is in the thermal equilibrium. But its decay later on is determined by the WIMP at the WIMPZILLA.
And another question is this forming WIMPZILLA will destabilize the scalar potential of phi. So it is very.
You mean the WIMPZILLA loop in the 2-point function of this phi? Okay, so I assume this phi includes all the things, and this should be regarded as the renormalization process. I didn't solve the hierarchy problem.
Sorry, is this phi the Euclidon or is it not?
No,
Oh,
this is
okay.
another particle.
Well, if no question, let's thank the speaker.